You've probably seen this before, right? You've got a plant, it's looking great, and then a vibrant green leaf starts turning a sickly yellow. Now, for you and me, that's a little frustrating, but for farmers growing high-value crops on a global scale, this is a massive, multi-million-dollar problem. So today, we're going to dive into the science behind this silent sickness and a really, really cool solution. So, when you see those yellowing leaves, what's your first move? More water, maybe? A different fertilizer? But what if I told you the problem is a bit of a paradox? What if the plant is actually starving for a nutrient that's already in the soil? It just can't get to it. Well, there's a technical name for this. It's called iron deficiency chlorosis. It's basically when a plant just doesn't have the iron it needs to make chlorophyll. You know, the stuff that makes leaves green and powers the whole photosynthesis show. And for big money crops like citrus or tomatoes, this isn't just a cosmetic issue, it is a major, major yield killer. Now, you're probably thinking, okay, easy fix, right? The plant needs iron, so just add more iron to the soil. And you'd think so. But here's where it gets really interesting. Farmers have been trying exactly that for decades, and a lot of the time it just doesn't work. The problem isn't about the amount of iron, it's all about its availability. Here's the heart of the problem. Soil chemistry can be a real bully. In a lot of soil types, especially the ones that aren't very acidic, iron gets chemically tied up or locked by other minerals. So the iron is physically there, but it's in a form that the plant's roots just can't grab. It's kind of like having a safe full of food, but you don't have the key. And this table just lays it out perfectly. On the left, you've got your standard iron salts. Their bioavailability? Super low because they get locked up so easily. And they really only work in a small window of acidic soils. But then you look to the right, at a chelated solution. It's promising maximum bioavailability and stability across all sorts of different soil pH levels. So, what in the world is chelation? Sue, how do you solve this locked safe problem? Well, you do it with some brilliant chemistry called chelation. This is the real hero of our story today. I love this analogy. Chelation, it's pronounced chelation, is a process where you wrap the iron ion inside a special organic molecule. This creates, basically, a protective ring around it. Think of this ring like a personal bodyguard for the iron. It shields it from all the hostile chemistry in the soil and personally escorts it all the way to the plant's roots so it can finally be absorbed. It's genius. And here is what that bodyguard technology looks like in the real world. This fine brown powder is called EDTA Fe. That stands for chelated iron potassium. This is it, a high-performance nutrient ready to dissolve and get to work. But here's the thing. This product isn't just about delivering iron. The whole formula is incredibly smart. It's been called a golden ratio because it's a dual-action solution. It's tackling more than one problem at the same time. Okay, so part one, of course, is the iron. At 12.4%, this chelated iron is the direct fix for chlorosis. This is the key that unlocks chlorophyll production, and it's what lets the plant quickly turn from that sickly yellow back to a healthy, vibrant green. But here's the second part of that 1-2 punch, 10.2% potassium oxide. See, it turns out that when a plant is fixing an iron deficiency, it often really needs a potassium boost too. And potassium is a total powerhouse. It activates enzymes, it regulates water, and it improves everything from how strong the roots are to the final size and even the taste of the fruit. So you're not just getting a green plant, you're getting a truly healthy plant. All right, so we have a nutrient that's always available and has this cool dual action formula. But for a modern high-tech farm, there's one more absolutely critical hurdle. How do you deliver it? And that brings us to the zero clog advantage. Just think about it for a second. Big commercial farms and greenhouses, they're not walking around with watering cans. They are using incredibly precise irrigation systems. We're talking drip tapes, micro sprinklers, foggers, all designed to deliver the perfect amount of water and nutrients to thousands, sometimes millions of plants. In that kind of setup, if your fertilizer doesn't dissolve completely, it clogs everything. And a clog isn't a small problem. It is a costly disaster that can wreck expensive equipment and starve your crops. So to prevent that nightmare scenario, there's an industry standard for purity. A fertilizer is considered high quality if the amount of stuff that won't dissolve, the water-insoluble matter, is at or below 0.1%. That's the bar. Now, get this. The EDTA Fe we're talking about, it tested at just 0.01% water insolubles. That's not just a little better than the standard. That is 10 times purer. And that tiny, tiny number has massive implications for how well this stuff works. And you don't have to take my word for it. This quote from an engineer says it all. This level of purity isn't just for a label, it's a functional necessity. It's the difference between a system that runs smoothly day in and day out and one that needs constant, expensive repairs. It's a guarantee that every single drop of that nutrient solution gets exactly where it needs to go. So who's really benefiting from this kind of precision technology? Well, we're talking about high-value operations, fruit orchards for things like citrus and apples, where iron deficiency is super common, commercial horticulture, think tomatoes and peppers that are really hungry for potassium, and of course, ornamentals and flowers, where perfect looks are literally everything. So it's pretty wild, right? We started with a simple yellow leaf, and we ended up with an ultra-pure, chelated, dual-action fertilizer engineered for the most advanced farms on the planet. It's an incredible example of how deep science is solving these really fundamental problems in our food system. And it leaves you with a final thought. If we can design and deliver nutrition this precisely for plants, what does that mean for the future of food and how we're going to feed the world?